In this presentation, I'm going to discuss the use of online techniques for fault finding on low voltage power cable networks. Finding faults on low voltage systems presents a number of challenges. Many of these can be overcome by using online monitoring techniques such as those provided by Kahui. In many low voltage applications, the cable is buried with underground T-joints feeding individual consumers. These are fed from alternate phases on the three-phase supply. This arrangement makes it very difficult to isolate sections of the cable without access to the consumer's premises. So why is fault location on these systems so difficult? First of all, the loads are permanently connected to the cable, and the lack of access to the consumer's premises means it's very difficult to isolate the cable. This makes the use of traditional offline fault location using surge generators impractical. In addition to this, there are multiple branches, any one of which may have become faulted, single-phase service cables, and, above all, we have the behavior of the fault. Faults on low-voltage systems may be grouped into three categories. Firstly, irregular voltage dips, which may be termed transitory. Then, repetitive fuse operations, which can be termed persistent, both of which are considered to be unstable. And finally, there are open circuits and solid welds, which are designated as permanent faults and are inherently stable. Many faults on low voltage cables begin as unstable transitory faults, which then develop into intermittent faults and ultimately may become permanent. If we can detect transitory faults early enough, a customer outage may be prevented. There are many different causes of faults on low voltage cables. However, unstable faults are generally caused by water entering the cable due to damage of the outer sheath. In a typical scenario, water enters the cable, creating a path between one or more of the energized cores and the sheath. The fault then ignites through the water, and the heat of the ignition causes the evaporation of the water, and the fault appears to go away. Over time, more water will enter the cable through the damaged sheath, and the process repeats. There may be significant time between one event and the next, ranging from minutes to weeks. Unstable faults produce non-sinusoidal voltages and currents, which affect the supply, often leading to complaints of flickering lights from consumers. Stable welded faults, however, produce sinusoidal waveforms, with the increased current leading to protection operation and a loss of supply. Stable open circuit faults result directly in loss of supply for customers beyond the fault point. Transitory faults are characterized by their appearance and disappearance, even within a single cycle. If we look at the evolution of the fault, we can see that initially it is not active and then it appears, then disappears again, and finally the system returns to normal. Such unstable faults can only be located using online methods with the cable energized. The Kahui system for low voltage cable fault location utilizes two different methods to locate faults. The first of these, time domain reflectometry, or TDR, uses reflections of injected pulses from the low resistance of the fault arc. The second method, transient recording system, or TRS, utilizes traveling waves which are created by the ignition of the fault arc on the cable. The TDR system works by injecting pulses into the cable under test. These pulses will reflect off features of the cable such as joints. However, they will also be reflected by the fault arc. If we consider a trace of the reflections while the fault arc is active and compare it to a trace when the arc is not present, the point where the two traces diverge represents the position of the fault. By measuring the time it takes for the pulse to travel to the fault position and its reflection to be received, and knowing its velocity of propagation, we can calculate the distance to the fault. The Kahui low voltage cable fault location system is designed around the TP23 unit. In this example, the TP23 has been located in a substation feeding the faulty cable. The unit will inject a TDR pulse into the cable every 500 microseconds and record the resultant waveforms, which are stored in a 64-segment cyclic buffer. When a fault is detected, the TP23 will trigger, and a selection of 16 pre- and 48 post-fault waveforms will be stored. These can be compared, allowing the distance to the fault to be determined. In order to measure the distance to the fault, we have to inject the TDR pulse into the cable under test. If, however, we simply connected between the phase conductor and the neutral, the TDR pulses will travel in all directions. This may include going into the bus bar and hence into all of the other cables connected to it. The result will be many reflections, which will make the traces extremely difficult to interpret. In order to be able to effectively identify the distance to the fault, we need to find a more efficient way of injecting the pulse. To avoid multiple reflections, the fault locator needs to be connected to what we call an open end. Such a position will only provide a single path for the pulse to travel along, so the distance to fault can be readily calculated. Suitable locations for the fault locator include the feeding substation or a link box. If the cable being tested is backfed from a remote point, it is possible to remove the local fuses in order to provide the open end we require. Connecting the TDR unit between the conductors and neutral will now provide a single path for the pulse to travel along. If the cable isn't backfed, we can simulate an open end through the use of a blocking coil. In this instance, we have removed one of the fuses and replaced it with an auto-reclose device, which is then connected through the blocking coil. This has the effect of stopping the high-frequency TDR pulses from travelling into the bus bar, but at the same time allowing the low-frequency power signals to carry on unimpeded. Again, we have achieved our open end, such that the TDR signals will only flow down the cable under test. Another method of obtaining an open end is to position the TP23 TDR unit at a normal open point in a link box. In this case, the cable is backfed from its normal supply point, such that it remains live and the supply is maintained for the consumers. In most cases, the use of TDR is effective in identifying the position of the fault. The big advantage of the system is that it only needs one device. However, as we've seen, it has to be connected to an open end, and this is not always practical. Furthermore, the range at which it can find the fault is limited by the attenuation of the TDR pulse within the cable, which is accentuated if there are a large number of branches. If any of these points mitigate against the use of TDR, as an alternative, we can consider the transient recording system, or TRS. The TRS system utilizes two TP23 units situated at either end of the cable under investigation. In the example shown, the length of the cable is designated as DAB. The first unit is installed in the substation and the other in a link box at the end of the cable. When the fault occurs, travelling waves emanate from the fault position and are detected by the TP23 units at each end of the line. Based on knowledge of the propagation velocity of the travelling waves, the units can calculate the distance to the fault from both ends. These are designated DFA and DFB. Prior to the fault occurring, the units at either end of the cable will be continually sending synchronizing pulses to each other. For simplicity, we will only consider the pulses being sent from end A to end B. The distance along the cable DAB is split into two parts by a hypothetical fault point. The distance DFA is from end A to that fault point, and the distance DFB is from the fault point to the end B. The time it takes for the synchronizing pulse to travel from end A to the fault point is TA, and from the fault point to the end B is TB. So the time to travel over the entire length of the cable is TA plus TB. Travelling waves have the same velocity as the synchronizing pulse. When the fault occurs, the travelling wave from the fault will arrive at end A in a time TA and at end B in a time TB. Hence, the difference between their arrival times is TA minus TB. Because they were both initiated by the fault, we know that this was the same instant in time, and so, by adding TA minus TB to the time at end A, we will synchronize the system by compensating for the time difference between the clocks of the two units. If we superimpose the traces from either end of the line, we can line them up at the common fault point. The difference in time between the departure of the synchronizing pulse from end A to its arrival at end B can now be redefined to correct for the lack of synchronization between the internal clocks of the two units. The time it takes to travel from one end of the line to the other is now TA plus TB, plus the compensation factor TA minus TB. This can be rationalized to 2TA, which is a quantity that can be measured. The distance to fault DFA is equal to TA multiplied by the velocity of propagation. This equation can be rearranged to include the term 2TA, which can be directly measured. The velocity of propagation of a cable is typically 54% of light speed, or 165 meters per microsecond. Having measured the value of 2TA, we can then calculate the distance to the fault from end A. If both ends have been sending synchronizing pulses, the same process can be used to calculate DFB, the distance to the fault from the other end. Settings of the TP23 and the analysis of the results obtained by the unit are carried out using a program called TP2X Master. This can be run locally on a laptop PC or on a tablet. Communications between the computer and the TP23 utilize Bluetooth signals, avoiding the need to have a direct connection, which would have represented an electrical hazard to the operator. If the TP23 is sited in an inaccessible location, or if it has been deployed for a long period of time, it may become inconvenient for the engineer to visit the site to download the data. For this reason, the TP23 is fitted with a SIM card, which allows it to communicate with the normal mobile telephone network. This facilitates access by a server, such as that provided by the iHost system developed by the Nortec company. The server can notify the engineer that the unit is triggered by means of an SMS text message or by email. This will then allow the data to be downloaded from the unit for analysis on a local computer. The system also allows settings on the TP23 to be changed without visiting the site. In summary, there are many reasons to use online low-voltage cable fault location systems such as the TP23. Low-voltage cable faults present a far greater technical challenge to power companies than their high-voltage equivalents. Penalties from the regulator are making it increasingly urgent to restore supplies after permanent faults and to improve power quality by reducing the number of intermittent faults. Alternative measuring techniques based on changes in impedance are far less accurate due to the variable impedance of the fault arc and the non-homogeneous impedance of cables of mixed cross-section. Accurate fault locations using the TP23 can eliminate unnecessary excavations, reduce costs and expedite the restoration of supply. For more information on this and Kahui's other fault location products, contact us at info@kahui.com. Thank you very much for your attention.